The final topic to cover about a heap is to talk about its implementation. And don't forget, you can definitely use the linked node structure that we covered earlier when we talk about a binary search tree. So remember, we actually got a class called BST node with the linked node structure. You can definitely use it to implement your heap, because heap, after all, is just a binary tree. On the other hand, given that a heap is a complete binary tree, that would mean we can actually use an array implementation with some very systematic indexing mechanism for the child and also parents. That's something I would like to speak about in this final topic related to the heap data structure. Right, let me just get right to it. Let's say we want to have this particular heap, right? You can see it's satisfied the relational and also structural property. I would say the array-based representation, which I'm going to go over with you, is not necessarily only applicable to a complete binary tree. For any general binary tree, you will be able to use the array representation, but it will just not be as space efficient as a complete binary tree. That's something I'll try to remark when we get to the visual. Just remember. And let's say this is the heap that we want to represent or to implement using an array. This will be the systematic indexing mechanism for the child and also the parents. Let's go over that. Given x can be either the root or some left child or some right child in the tree. And let's go over the principle and then we'll see the example right away. We'll try to construct this particular tree, a heap, into an array representation. We are turning nonlinear into linear. That's basically what we're doing. The root will simply got the index 0, always. And then for any left child, its index will simply be the index of its parents times 2 plus 1. For any right child, in order to store that, the index of it should be the index of its parents times 2 plus 2. That's the mechanism. Simple and straightforward. Let's see how we can apply this mechanism to really transform this nonlinear data structure, a heap, into a linear data structure array. Let's see how we can do that. Right, so I just put the mechanism over here to remind you over here. Let's first of all work out the exact indices that we need to put into the array. Number one, the root is going to have, oh, you know what? Let me just use the red, because root is actually so special. The root always has the index 0, meaning that the root over here index is going to be 0. And then all the left child is going to be its parents' index plus 1. 2 times and then plus 1. 2 times 0 plus 1 is going to be 1. 2 times 1 plus 1 is going to be 3. 2 times 3 plus 1 is going to be 7. Right? So you can see so far we got 1, 2, and 3 left child nodes already. Right? You can see the numbers obviously are odd numbers. Right? Let's talk about some right child, and then we'll finish the rest of the left child as well. Let's say for the right child, it's going to be, according to definition, 2 times the index of its parent plus 2. 2 times 0 plus 2 is going to be 2. And another right child. 2 times 2 plus 2 is going to be 4. Oh, beg your pardon, 6, of course. And what about this right child? The parents, 1, 2 times 1 plus 2, 4. How about this right child over here? 2 times 4 plus 2, 10. And let's see, I think we have to fill in, oh, actually, over here. How about this right child over here? 2 times 3 plus 2, 8. And let's fill out more left child. What about this left child over here? 2 times 2 plus 1, 5. And what about this left child? 2 times 5 plus 1, 11. And also, 2 times, how about this left child? 2 times 4 plus 1, 9. Finally, what about this right child over here? 2 times 5 plus 2, 12. Now, surprisingly, I'm pretty sure you have observed, it's going to go like this. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. This will be how you can understand it visually. However, to really make it work algorithmically, I would suggest you actually get used to how I actually figure out the left child and also right child nodes. Right? It's either way works, but you just want to see which one might be more relevant to what you want to achieve. That's about the indices for different individual nodes over here, and accordingly, we can store them into the array, right? Let's now do that quickly. So the first one is going to be the root 4C, right? You can see over here. And you got left child and right child. So the left child is this one over here, 5A. And its right child is 6Z. And for the next one is going to be 15K. And the next one is 9F. Let me fill out the complete tree over here because I want to make some more observation together with you. And then 7Q and 20B. We're getting there. And then 16X. Yeah, just notice about the color. Every blue elements are the left childs. Oh, beg your pardon. Every green nodes are the left childs, and every blue node is the right child. 25J, and also 14E. And 12H, 11S, and finally 13W. I will have some exercise for you right away. You can think about it. Exercise. What if the binary tree that we are trying to represent is not complete? Especially, why is it bad? For space utilization. Right, that'll be the hints for you. For example, for the tree not to be complete, for example, let's say maybe for this part of the subtree, it simply doesn't exist. In that case, it wouldn't be complete anymore. Or let's say we are trying to fill out the bottom nodes over here, not really strictly from left to right. Maybe we actually miss maybe some nodes over here and we got more over here, for example, right? So that'll be the exercise for you to think about. Okay, and let's now talk about some extra observation. Apparently, you can see this one over here is level 1. This part here is level 1, right? Level 1. And you can see level 1 can be seen from over here. That is level 1. Okay, I'll just say L1 for short. What about level 2? Level 2 is actually over here. We got more nodes, obviously. And this part over here is level 2. And if you want to find out level 2, starting from 3 all the way to 6, that'll be level 2. And of course, the remaining ones are the bottom level in this case, right? That's something you can also see. Think about the array that you actually ultimately obtain as the representation for the binary tree. It's going to be starting from the root, and there you guess the next consecutive cells of the array is going to be one level, and then the next consecutive block is going to be next level, and etc. So the bottom level should be about over here, right? From the ending part of the array. All right, that's the observation I would like to make right away, and let's now go back to the slides. I think there are some nice facts which we want to go over quickly, and that'll be it. Where are the nodes at levels 0 up to h-1, except for the bottom level, stored in the array, right? Don't look at the answer just yet. I would like to work out the answer together with you quickly, right? You can think about in this particular binary tree, right? Oh, you know what? Let me just draw the general tree for you. Let's say this is a general complete binary tree. Let's say this is the bottom level, level H. How many nodes do we have from level 0 to level h-1? Level 0 to level h-1. This part over here will be level 0 to h minus 1, the number of nodes is something that we spoke about earlier as the property, right? It's going to be 2 to the power of h minus 1. And to really see why this number will be the case, you should really refer to the earlier lecture recording. Okay? Since we know there should be in total 2 to the power of h minus 1 nodes in this part here, given that we start with the root being index 0, what should be the index for the last node over here? Well, given that I start with 0, right? So you can think about this one here, right? Everything should be made logical to you. You can think about this node over here is index 0. And I'm talking about the very last node over here. What should that be? Well, given that the number of nodes is 2 to the h minus 1, and we start with 0, that should be 2 to the power of h minus 1 minus 1. Right? Always the last index of the array plus 1 will correspond to how many elements are there in the array. Right? That's something you want to remember. This will be the first observation, the first fact. 2 to the h minus 2. All right? And you can definitely plug in the number and find out. For our particular example, this will be the index range for all the levels up to, but excluding the last one. You can see it will be from 0 all the way to 6 over here, right? 2 to the h. The h will be 1, 2, and 3. 2 to the h will be 8. Minus 2 will be index 6. So that's exactly the facts that we can confirm. Question number 2. Where are the nodes at level h stored in the array? That one there is more like a follow-up question over here. Since we know this particular node here has the index 2 to the h minus 2, so we would know what would be the first node at level h. Accordingly, what about this? Well, this one here will simply just follow this, right? So that'll be 2 to the h minus 2 plus 1. 2 to the h minus 1. Right? You can see, for example, this is index 6, and this will be index 7, right? Just plus 1. And let's say, for example, the last node. Let's say we go with several nodes over here. Let's say this is the very last node for the binary tree for now. In that case, what will be its index? What will be the last index? The last index will be the number of nodes minus 1. You can see we got 13 nodes in total over here. Right? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. We got 13 nodes over here. That's why the last index will be 12. Right? So that will be exactly n minus 1. So this will be the range of indices for level h. But you can see how useful it is to really have an abstract perception of the tree. So you can work out many nice formula quite easily. Right? So that's what we just talked about. And you can definitely check about this number over here. It would be simply from 7, which corresponds to this, and also 12, which is the number of nodes, 13 minus 1. Right? We got 2 more to go over. How do we determine if a non-root node is a left or right child? Well, that one's rather easy. Right? You can see these are all the right child. Let me just highlight them. All the left child. These are all the left child. Left, 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 and left. Left, 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 and also left, left, left. These are all the left childs. And what's the commonality between them? Well, odd numbers, which is not surprising because it's going to be 2 times some number which is guaranteed to be even, and then plus 1, which is guaranteed to be odd, right? Very simple manipulation for the math. What about right child? Well, right child over here, right child over here, and right child over here, right? You can see in that case, well, I should have used blue, shouldn't I? Let's see over here. Right, over here, right, 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 and right. They'll simply correspond to all the right child over here, right? You can see I'm excluding the root. And in that case, they're all just even number, which makes sense. 2 times the sum index will be guaranteed to be even, plus 2 guaranteed to be even. Right? That's easy to answer. Final question. Given some node x, that's not a root, how do we determine the index of their parents? For example, you can see if you can see these two nodes have the same parents over here. If I'm given the index over here, first of all, I know it's odd, so that means it's a left child. In that case, how do I get its parents? Simply just -1, right? Actually, not just -1. Let me be more careful, right? So apparently, this is a left child, right? The parents is going to be 3 minus 1 divided by 2. That'll be the formula. And also, you can see this one over here will be the right child. And what about its parents? It's going to be 4 rather than -1. It can be -2 divided by 2. You can think about what we're doing over here is exactly the reverse manipulation of the calculation for the child indices, right? That's something you can look into further, right? That'll be exactly the formula you have to follow. All right, that's about everything you should know about the array-based implementation for a binary tree in general. Of course, in order to be space efficient, which I post as an exercise for you to think about, you better make sure the tree is complete binary tree. Of course, there'll be nothing to stop you from using the array to really implement a general, just implement any arbitrary binary tree, which may not be complete. You just have to know what the trade-off is about a space. Alrighty, so that's about everything I want to talk about for this lecture here about priority queue, heaps, heap sort, and also array-based implementation for a complete binary tree. And that's about it. Alrighty, and I think that's about everything I want to cover in the course, and there will be one more wrap-up lecture to conclude about this course. Just stay tuned and watch that video.